we have to start with quantization of charges. So quantization, I'll just give you one simple example of quantization in our real life. Then we can move forward. So quantization means what? Any quantity, any amount of quantity, when we are able to express that amount of quantity in terms of some integral multiple of unit, okay, some basic unit. So when we can express, so first I'll talk about quantization of the charge. So when we can express a certain amount of charge, okay, in terms of integral multiple of certain unit, basic unit, and that we denoted as E. Okay, that basic unit we have taken as E. E is the charge, like magnitude of electronic charge or protonic charge. Magnitude of electronic charge, okay, or proton, charge of proton. Magnitude of electronic charge or charge of proton. Both actually have same magnitude, and as I mentioned that day, if it is electronic, if I take the magnitude of electronic charge or protonic charge, this will be 1.6 into 10 to the minus 19 Coulomb. Okay, so when we can express any quantity, not only charge, suppose I have 100 rupees, okay, so how do I express this? What is the basic unit? Paise, right? So 100 rupees, I can 1 rupee, 10 rupee, like that I can express. But suppose I have 1 rupee alone. So how do we express 1 rupee? 1 rupee we can express as 100 paise, right? Paise, like that, right? So 100, this paise is actually the basic unit, and this is the integral multiple. This is a number. 100 is a number. Similarly, if I say 100 rupees, I can express in terms of 1, okay, 1 rupee into 100, okay, in terms of 1 rupee unit. So that case I can take the basic unit as 1 rupee. I can take 10, that case 10 into 10, that means 10 rupees is the unit basic unit, and there you have to take 10 of 10, like you have 10 rupees note, some 10 rupee notes, that will give you 100. So you can understand now that any quantity, quantization, not only this exists for charge quantization. So quantization, this term will come again in your physics, like quantization, like this is charge quantization. There will be many other quantities are there, like energy quantization will be there. Energy, now you know, like a discrete in this continuous term, okay, continuous. Then you will see discrete levels. You see in the Bohr models, you will see discrete levels. This is called energy quantization. Okay. What I wanted to mean is, suppose I'll just give you a simple example. Another example. Suppose you have a bag full of uh, wheat flour. Okay, wheat flour. Okay. So can you count one by one like that? Can you count this? No, right? You cannot.
No,
But if
sir.
I ask, no, suppose you have rice, at least you can count one by one, right? Grain one by one, you can count. Okay, rice, leave rice. If I say potato, you can count at least, right? Isn't it? So some quantities are there, okay, some quantities are there in nature which we cannot count 1, 2, 3, 4, 5, like water. Water we cannot count 1, 2, 3, 4 like that, okay. Maybe we can say in terms of chemistry
Stars.
how many molecules will be there. Starch, yes. So kind of those we cannot actually count one by one. But such quantities are there, few quantities are there we can count. So similarly, in case of charge also, initially it was thought that charge can be a quantity which we cannot count 1, 2, 3, 4 like that. Okay, 1, 2, 3, even this 1, 2, 3, 4, these are actually the integral number, integer number. You have to have certain basic unit also. You have to suppose I can write 1, 1, 2, 3. These are the integer numbers. 2, 3, 4. These are integer numbers, right? These are integer numbers. Along with that, I have to have certain basic unit. Like I said, suppose 100 rupees you have. 100 rupees you have. Arrange 100. So you can express this in terms of the integral multiple. I'll take 10. Then what will be the basic unit? 10 rupees will be your basic unit. 10 rupees will be your basic unit. So, so you can see that this rupees actually a quantized it is quantized. Quantized means you can express it to like expressed by multiplying an integer number or integral multiple. You can express as integer into, suppose this is n into 10 is equal to 100. So what is n? You can find out how many 10 rupees notes are there. So you will be seeing that you have 10 rupees note. If I say this basic unit is 5, then basic unit is 5. So that will be n into 5 is equal to 100. So how many 5 rupees note will be there? 20 numbers. This is number. Okay. So that's how in charge also it is seen that experimentally it is seen that charge can be expressed as integral multiple of a basic unit, but this basic unit is constant. In this case, suppose in case of rupees you can change your basic unit, okay. In case of your other things you can change your basic unit, but in this case basic unit is not changed, okay. The basic unit has been taken as E. What is the E? So I can write any amount of charge, q1 here, q1, it is q2, suppose any amount of charge I can write in terms of integral multiple. This is the integral integer number into basic unit, that is E. Okay, so charge is equal to q. So in your book it is written q is equal to ne. That means what? This is the basic unit, E is the basic unit of charge, okay, and this is integer number. Any amount of charge you can express in this way, integer. So now let us take one example that day also we had taken. Suppose I have 1 coulomb charge, q is equal to 1 coulomb. Can you tell me how many electrons are there or how many basic units are there here? 1 coulomb charge, how many electrons are there? I am taking as electron as or electronic charge as a basic unit. If this is my basic unit, so how many E are there? Basic unit. So it will be written how many electrons are there in this 1 coulomb charge. So I have to, what I have to write? I have to write total Q is equal to Q is equal to N into E. Integer number I have to find out, and this E I know. So you look here, N is equal to total charge given by the basic unit. So total charge how much? Total charge 1 coulomb is given. And what is the basic unit? 1.610 minus 19 coulomb. So this goes, so you will get a number. Okay. So you will get a number. So how much will be that? This will be actually of the order of 10 to the power minus. So if I say exact number, then it will be 2.6 into 10 to the minus. Sorry, this will be your, okay, no, this will be of the order of 10 to the power 18 actually, 10 to the power 18. some factor will be there in this case. So I can just write it, just a minute. So it will be into this 6.25 into 10 to the power 18. Okay, so this will be 10 to the power 18 order. You can see this many electrons will be there. How many electrons will be there? 6.25 into 10 to the power 18. This is a number. Now, if suppose you are told that there are n1 number of electrons are there, n1 number of electrons, numbers of electrons, okay, electrons, and there are n2 number of protons. So what is the total charge? Can you tell me what is the total charge? So total charge will be n1 into charge of electron. You have to take now with the sign, okay, n1 into minus of that, and plus this will be n2 into E. E is a charge of photon I have taken. So see now it will be your E into n2 minus n1. This will be your total charge. Okay, this is from the quantization. Understand? Now is it clear? Is it clear? Nikhil, is it clear to you now? Priyadarshini,
Yes, sir.
is it clear to you now?
Yes, sir.
Okay, so any amount of charge you can express in terms of integral multiple of some basic unit. That basic unit has been taken as E. E has value, if you take positive, that is 1.6 into 10 to the power minus 19, and minus if you take electronic charge, then minus 1.6 into 10 to the power minus 19. Okay, this is all about your quantization. Now we'll just move on to today's topic, that is Coulomb's law. Look, Coulomb's law is a law which actually measures the force between two charges quantitatively. What is that? Quantitatively. Quantitatively means it can exactly tell you how much Newton force is there in between two point charges. So what is Coulomb's law? Are you able to see my screen properly?
Yes, sir.
Okay, I'll increase a bit. See, Coulomb's law is a quantitative statement about force between two point charges. Now you might be thinking, sir, point charge means what? Point charge means, see, in this universe, Coulomb's law is applicable everywhere. We'll see. Coulomb's law is applicable from massive body to even subatomic particle. That we'll see. Now, point charge. What do you mean by point charge? First of all, what is point charge? So, can you tell me what is point? Point does it have any dimension? Point does not have any dimension in general. But when I say point charge, so then I'll say point charge means it does not have dimension, but it has certain amount of charge. Certain amount of charge and mass. It does not have dimension, but it has certain amount of
Electrons are
charge and certain amount of mass. Yes, electrons and photons. Tell me, yeah. Priyadarshini, you wanted to say something?
Yes, sir. Point charges are that only, no, sir.
Yes, actually electron, proton and other subatomic particles which say point charge. Even sometime you will see a sphere also will be taking as point charge. Okay, but how is it possible? It has a dimension. That's what I am going to explain. Okay, point charge, obviously electron is very tiny, so it has like radius very small, and proton also has very small radius. That I can say is a point charge. But after some time we will see that force like sphere 1, sphere 2, So I will just consider them as point charge. How is it possible? Okay. So see, and Coulomb's law will be applicable for bigger, not even point charge. It will be applicable for this spheres also. Okay, this spheres which is finite dimension. So how these are point charges? That is what I'm going to explain. So point charge does not mean that it does not have dimension at all. It may have dimension, but point charge in the sense the distance between two charges. Okay, the distance between the two charges is, suppose this is d, and their radius is, suppose they are identical. Here I am taking their radius is r1, okay, or r. Both cases it is r. So these charges will be considered as point charges when my d is much greater than r. That means compared to their size, if the distance of separation is much greater, then I can consider these two quantities or these two charged entities as point charge. Understand? Okay. So this is the assumption. Okay. This is the assumption. This is assumption. And actually he had deduced the expression for Coulomb, like forces between two charges, thinking as point charges, but later on it is applicable for any charge distribution that we will see later. Okay, as you go along with this chapter. So now what he had done, actually, how did he like concluded, or how did he deduce this law? Actually, he had invented, or who had invented? Charles Coulomb. It is Charles Augustin de Coulomb. He was like a military man, military engineer in his early career. Okay, and after his retirement, he started scientific research. So he invented torsion torsion balance. Torsion, sorry, this will be S. Torsion balance. Okay, what he invented? Torsion balance. So with this torsion balance, he could what is the use of this torsion balance? The use of this torsion balance is to measure the force between, directly. It can measure the force directly. Okay, measure force between two charge entities. Measure forces between two charges. So he invented an instrument which is called torsion balance. Okay, I'll write once again, torsion balance. So this is not there in your syllabus, like in your textbook. What is torsion balance? So I'll request you to see some YouTube video. What is torsion balance and how is it working for measuring force? If you don't understand, you message me. I'll just uh, tell you in the next day what is torsion balance, how it works. Okay. Next day I can tell you if you.
Sir, it was invented by Coulomb, sir.
You just see some video first. Sorry.
It was invented by Coulomb,
Yeah, tell
sir.
me. Yes, Coulomb. Yes, Coulomb. Charles Coulomb. Sorry, Charles Coulomb. Okay. So same person who has invented this law, Charles de Coulomb, Augustin de Coulomb. Okay. Uh, so he has invented the force between, like, what will be the force between two point charges? If suppose there are Q1, there are two charges Q1 and Q2. Okay, and they are separated by a certain distance r. Okay, r. Then what will be the force between these two? He has invented this. How did he invent it? Actually, he could directly measure the force between two spheres. Okay, metallic spheres he had taken. One is charged, another is uncharged. Like that, it is a little bit discussed in your textbook. You can see that. I'll just tell you the main fact over here. Okay. So what he had proposed in his law that the force, Coulomb force between two charges Q1 and Q2 which are separated by a distance r, the force between them is proportional to the product, like directly proportional to the product of the charges Q1 and Q2, and it is inversely proportional to the distance between the charges. So this was his observation, and he stated that the force will be then, see, if I just write a k constant, then q1 q2 by r square. So this is directly proportional to the product of the charges and inversely proportional to the square of the distance, and if you write in terms of vector, then I can give you r cap here. Okay, I can write r cap. Okay, now see, this is a proportionality constant, and this proportionality constant actually found to be having value 9 into 10 to the power 9 into 10 to the power 9 Newton. Okay, it has unit of force, and it is seen that it can be expressed in terms of 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught, and this epsilon naught is actually called free space permittivity. What is this called? Free space permittivity. This is called free space permittivity. PERMITTIVITY. Free space permittivity, and it has a value 8.854 into 10 to the power minus, I think, 12, and it has so what will be the unit we can find out from here actually. Okay, we can find out the, see, this is Newton, right? So I can find out the unit from here. If this is Newton, see, this is q1 q2, so Coulomb square, so it will be Coulomb inverse. Okay, because it is this, and then meter square, and this is Newton per Newton, like that it will be having unit. Okay, so it is, see, it is written in your book also. Yes, so it is here. Okay, and how did he arrive this conclusion? What he had done actually, he had taken a metallic sphere having charge q. First he had taken a metallic sphere here having charge q, then he has taken another identical uncharged sphere and put it in contact so that the charge will be distributed equally to this sphere. So charge will be in both cases q by 2, q by 2. If he brings another sphere, it can be again expressed in terms of q by 4, etc., like that. Now what he had done, he has measured the force keeping two charges equal charges, then keeping two unequal charges, and at that time the distance he has not varied. Finally he had varied the distance when the charge were kept same. Like that, there are various various observations he had done, and from there he could deduce this law. This is called famous Coulomb's law, and this Coulomb's law he had actually described for microscopic particle. Now see, he had taken for described it for point particle, but later on it has been applicable for subatomic particle as well as gross material like spheres also. Okay, and you can see this unknowingly Coulomb has discovered his law, okay, which can give you the magnitude of the charge. Actually that time the charge was not known. When he had discovered this law, the magnitude of the charge was not known actually. but he can give from his experiment, he can give the unit of the not experiment, from his law, he can give the unit of the charge. I'll just tell you how he can give the unit of the charge from his law. And we have to know which direction the force will be acting. Okay, we have to know in which direction the force will be acting. The force will be acting along the line of that like separation. Okay, along the direction, they like along the direction of their separation, or I can say along the direction or along the line joining the two charges. So the force will be acting along the line joining two charges. So if my charge is here, one charge Q1 is here, if my another charge Q2 is here, so the force will be acting along the line. The force, direction of the force will be parallel to this. Now I'll tell you, there are two kind of forces. As you know, there could be positive and negative charges. There could be positive and positive charges. That I'll just come to that point just after a while. So what I was going to say, that from the Coulomb's law, itself, the unit of the charge can be obtained. See, I have got this as K Q1 Q2 by R square. This is the Coulomb's law. So this can be chosen any arbitrary number, but this is constant, proportionality constant. So but this has been chosen in such a way that it has value 10 to the power 9 Newton, which is actually written again as 1 by 4 pi epsilon naught. So if this is actually see, this is 9 into 10 to the power 9 Newton, then see, if I just take Q1,
Sir,
yes,
which screen you are showing, sir?
my presentation, are you not able to see?
Sir, it was on before screen, sir. Now
Okay,
only
I'll
it
raise
came.
it. It has come, right?
Yes, sir.
Now, are you able to
Now
see?
it is not there, sir.
Are you able to see now?
No,
Fine.
sir.
Is it there? What is not there? Okay, I'll just come back then. Okay, I'll just reshare. Okay, I'll reshare. I hope you will be able to see now. Are you able to see the now?
Yes, sir.
Is it visible now? Is it visible?
Yes, sir.
Okay. So this was the Coulomb's law, right? This is what I have written. And this proportionality constant has been found out actually as 9 into 10 to the power 9 Newton, which is again expressed as 1 by 4 pi epsilon naught. Okay. So epsilon naught, I told that time that this free space permittivity has value 8.854 into 10 to the power minus 12, right? This is Coulomb to the power minus 2 meter, yes, meter square and per Newton. Okay, per Newton. It is the unit of this. Now see, if I say Q1 is 1 Coulomb and Q2 is also 1 Coulomb and R is 1 meter, then how I get this will be K, right? So from here I can define the charge. So this is actually 9 into 10 to the power 9 Newton. So I can define the unit of the charge. How I can define? So 1 Coulomb will be like such that. So if I keep 1 Coulomb charge, if I take 1 Coulomb charge, both Q1 and Q2 as 1 Coulomb and keep them how much? At 1 meter distance. Okay, 1 meter distance. If I take 1 Coulomb here, 1 Coulomb, and keep them at 1 meter away from each other, then the force of repulsion, if these are positive, then it will be repulsion obviously. This force has a magnitude of 9 into 10 to the power 9 Newton. That means I can say, see, if I keep two charges, okay, 1 meter away, and if the force between them, okay, the Coulomb force between them is 9 into 10 to the power 9, that amount of charge can be told as 1 Coulomb. Understand? See, in your book it is written very nicely. I'll just I'll just go to your book. It takes some time actually. I can change immediately, but it will take, since it is like online platform, it will take some time to change the screen. Are you able to see the book now?
Yes, sir.
Okay. See how the unit of the charge can be defined from Coulomb's law. That is, one Coulomb is the charge that when placed at a distance 1 meter from one another, like from another charge of the same magnitude in vacuum, an electric force of repulsion of magnitude 9 into 10 to the power 9 Newton. Okay, 9 Newton will be there. Okay, so this is actually, so the force of repulsion will be 9 into 10 to the power 9. When that much amount of charge is called 1 Coulomb. Okay, then you can understand this is the 10 to the power 9 Newton means it's a huge force. That means the Coulomb is a very big unit. The charge Coulomb, see, Coulomb is a very big unit. So in practical, what we use millicoulomb, microcoulomb. Okay, in our practical use, we use a smaller unit. So micro means what? 10 to the power minus 6 Coulomb, and millicoulomb means 10 to the power minus 3 Coulomb. Okay, so 1 millicoulomb means 10 to the power minus, how much? 10 to the power minus 3 Coulomb. Okay, and microcoulomb means 10 to the power minus 6 Coulomb. Okay, so this is about the force. Now we'll see how we can write in terms of vector. So force is a vector quantity, right? It is a polar vector. That means it has a point of application, right? So look, I have two charges Q1 and Q2. Okay, suppose they are located, I'll just go to my presentation, there it will be better. Is my presentation visible?
Yes, sir.
Okay, so now what I'm going to write, now I am going
Yes, sir.
to write the force as a vector. Okay, force as a vector. Okay, I am going to write force in terms of vector. See, I think, see, this is a vector quantity, so I have to give a vector direction. Okay, in which direction force? Suppose I have positive seat Q1 charge here and Q2 charge here, and they are, see, from an arbitrary origin. See, this is the origin. So Q2 is located at R2. This is the R2 vector. Okay, I am writing again, and this is R1 vector. This is a position vector. You know, guys. You guys know, right? What is position vector? The distance from the origin is called position vector. Okay. Okay. So Q1 is at R1 and Q2 as R2. So what will be the distance between them? I will write in terms of at like law of triangle of addition. See, I have a vector. See, this vector. So these two vectors I have. So I can write in terms of law of triangle. So how I can write? So suppose this is R1 to R2 1, whatever I can say here. I'll write R2 1. So if I write this is R2 1 vector, so I can write, see, I can write R1 plus R2 1 is equal to R2 vector, right? According to my law of triangle. See, this is R1, this is R2 1, and this is my R2, right? I can write R1 plus R2 1 is equal to R2, right? This is the one. Okay. Now what I can write as R21? R21 from here. R21 I can write as R2 vector minus R1 vector. This is simply from law of vector, law of triangle of vector addition. From there we can write this. Okay. R2 is equal to R21 is equal to R2 vector minus R1 vector. Okay. Now look what I am going to write. I'll write this force in terms of vector. Okay. So see, in this case actually in the Coulomb's law, the magnitude of the force, see this magnitude of the force is same for, see, if I say what is the force experienced by charge q1 due to q2, the magnitude is the same. What is the force experienced by q2 by due to q1, that also has the same magnitude, because see q1 q2 by r square. This is the factor, and this is a constant value. This has constant. This is a constant. So see q1 q2 by r square. This is not changing. If I say what is the force experienced by q2 due to q1, that is also same. And if I say the force experienced by q1 due to q2, that is also having the same magnitude. So magnitude is same. Okay. But only thing is in which direction force are acting. That is the main thing here. See. So if I write the force on charge q2 due to 1, this is the notation. So this is what force on, I'll write here, force on q2 charge due to charge q1. That notation is written as that, this q21. And if I say what is the force on q1, that means I'll write 1 due to 2. So this is force on q1 due to q2. Okay. So these are the notation. Now look, this will be repulsive force. Repulsive means what? They will be pushing each other. Pushing each other. Repulsion means pushing. So repulsion means pushing each other. So see, the force on this guy Q1 due to Q2 will be what this one. So it will be pushing this way. And force on Q2 due to Q1. So Q1 will be pushing Q2 this way. Right? But the magnitude will be the same. So the magnitude will be the same, but their directions are different, opposite to each other. So I can say, see, this is actually somewhat Newton's third law, right? They will be pushing or pulling each other with the same force. Okay, Newton's third law. Right, it is kind of Newton's third law. It is actually what is that called? It is satisfying. It is satisfying Newton's third law. So you can understand now that F12 magnitude of F12 is equal to magnitude of F21. Is it clear now? So now what I can write is, see, if I write F21, how do I write in terms of vector? Q1 Q2 divided by 4 pi epsilon naught. R square means what? R21 square, R21, okay, square, and this will be having unit vector along R21 direction, right? Unit vector. So see, any vector I can write by its magnitude, and see its magnitude is this one. This is magnitude of the force. And what is the direction? R21. What is the R21 direction? The R21 direction is this one. So this is unit vector, right? Understand? So this is actually vectorially this I can write in this way. Vectorially I can write in this way. If you want to write this as vectors, then you have to multiply here 1r. See, in your book maybe it is written in another way also, like this. See, this I can write even q1 q2 by 4 pi epsilon naught r21, okay, whole cube, and I can write this as r21 vector. Is it okay for you? Is it okay for you? Is it okay for you? Do you understand this?
Yes, sir.
Yes,
See,
sir.
because see, this is I have written cube here, okay? R21 cubed, okay? To the power 3. Is it all right? Yes, it is all right because see this R21 vector I can write as R21 magnitude, right, into R21 cap. So this one will get cancelled with the other one here. So you'll get eventually this one, okay? Either you can write in terms of cap, okay? I'll clear it and then again write. See, F21 I can write even, see, 1 by 4 pi epsilon naught Q1 Q2 by R21 square, and this as R21 cap, or you can write Q1 Q2 R21 cube, and this as vector. Okay, these are two ways of writing the vector, the force vector, Coulomb force, but they are actually the same. This is actually cube, okay? This is cube. Hope you understand. If I write F12, see magnitude and unit vector you have to write. So magnitude is same for both Q1 Q2 by 4 pi epsilon naught. Okay, now if I write R12 square, if I write R12 square, okay, then what I have to write here? I have to write R12 cap, right? But is it, see, R12 and R21, which direction it is? See, R21 I have defined R2 vector minus R1 vector. So what will be R12 then? If I just take minus over here, then R1 minus R2 vector. So this I can write as R12. So if you write in terms of 1, 2, then you have to give minus R12. Okay? Understand? So you have to give a minus R12 here. Or if you write R21 also, you have to give minus. Okay? See, R21 is this way and R12 is this way. Sorry, if you write R12, then it is fine. Only this you can write. Or if you write R21, then you have to give a minus sign. You have to define that. You have to tell that this is R21. In this direction, R12. Okay, in this direction it is R12, and this direction it is R21. So basically, R21 vector is equal to minus R12 vector. So you can understand that these two unit vectors are actually in the two opposite direction. Okay, that means they are repelling each other. I can write, see, F21, I can write Q1 Q2 by 4 pi epsilon naught R21 square R21 cap plus R, and F21 I can write. So this I can write, see, this itself I can write. If I just take a minus, if I just take Q1 Q2 by 4 pi epsilon naught R12, Okay, then I can write here minus R21, right? R1 to R21 square is same. So I can write even R21 also here. Okay. Understand? This will be nothing but F12. Okay. So with the minus sign. So F21 is equal to minus F12. So better to write here 1 2 itself. Okay. For the other force, if I write 1 2, you have to write here, and this 1 2 R1 2 square will be equal to R2 square to 1 square. These are same. So I can write as F21 is equal to F12. Now this is for the positive case. If I have two negative, one positive, another negative, so they will be attracting each other. That means what? You look here. So this is Q1 and this is Q2. So the force, I said, the force on the charge Q2 due to Q1. Okay. So which direction the force will be? See, this is negative. See, this is negative charge. Q2 is negative here and Q2 positive. Both will be pulling each other. Pulling each other. So see, the force on charge 2 due to 1 will be in this direction. Okay. That means 1 is pulling the charge 2. Okay. This is F21 direction now. So what will be the direction of F12? So F12 direction will be this way. Okay, see this one, F12. So earlier F12 was this way. This was repulsion. So repulsion means this way and this way. And attraction means this way and this way. Okay. This is attraction. And this is repulsion. Okay. This is repulsion. So suppose I have a positive Q charge over here. I have another negative charge Q. If I say what is the force experienced by small Q charge? What is the force experienced by small Q charge and what is the direction of the force? So see, magnitude you know, but direction will be this way. Okay, direction will be small q to capital Q. This direction it is pulling each other. Okay, and what will be the force on capital Q due to small q? So that will be this way. Okay, this is F capital Q and this is F small q. Okay, this is the direction of the force. Now look, this direction is very much important because we will be solving few examples in your book which are actually depending on this knowledge. If you have this knowledge very found, like very strong, then you'll find that the examples are very simple to solve. Okay, so this is, suppose I have, okay, one more point I need to tell you, that we know, see here, this force is called inverse square law. This is actually, this force is actually a inverse square force. What is this force called? Inverse square. That means, see here we have seen this will be Q1 Q2 by 4 pi epsilon naught r square. R square. R is the distance between the point charges. Okay, so it is actually inverse of the square of the distance. That's why this force is called inverse square law. This actually called inverse square law. This Coulomb's law is called inverse square law. So can you give me such another such law which you have learned in your 11th standard, which is also varying as inverse square inverse or inverse square law? So this is electrostatics. This is electrostatics, inverse square law of electrostatics. And we have, I think you have learned inverse square law gravitation, right? Gravitation. In gravitation, right? Gravitational force. What is that? In between two masses. If this is M1 and this is M2, then what will be the force? And it will be given by minus sign. Minus means attraction and see positive means repulsion. And see in between two opposite charges it will be attraction, so it will be minus. Okay, between two different charges it will be minus. Force will be minus, having a sign minus. Okay, so in this case also it will be minus. This is the universal gravitational constant G m1 m2 directly proportional to the masses and inversely proportional to the square of the distance between the masses. So this is also called an inverse square law. This is also inverse square law. But there is a difference between these two. Can you tell me what is the difference between these two forces? So there are two forces here actually. In case of electrostatics, you can have attraction.
Repulsive force and attractive force, sir.
Right. You will get two, repulsion and attraction. But in gravitation, you will get only attraction. Okay, only attraction for gravitational force. Okay, only attraction. So this is the difference. Now one more, not more, it is most important difference. Can you tell me if I write this electrostatic force as Fe between two charges, and if I say gravitational force between two the same mass. See, if I say two electrons, okay, if I say two electron or one electron and one proton, so suppose this is electron and this is a proton, okay, this is also positive, so this has negative. Okay, I'll just, so yeah, so it has negative charge. This is electron and this is proton, okay, positive charge, okay, E and this is P, and they have, see, they have also some mass Me, and they this, so Me is the mass of the electron, this is mass of the proton. Okay, so you can see this between the electrons there are two forces acting. One is electric force, another one is gravitational force. Can you tell me which one is greater? Which one is a greater, having greater magnitude? Which one is greater? Okay, among these two. I mean to say, what is the strength? Like strength wise, which one has more strength? Whether the gravitational force or the electric force? It is the electric force which has actually greater magnitude. Okay, greater magnitude. We will see in your book there is a very nice example. Okay, very nice example. You look here. You can even do by yourself also. Sometimes they will ask you to find out what is the ratio between electric force and gravitational force. That is one question actually. In exam, generally they ask. So you can note this example. This example is very important example for your exam also. Okay. See the Coulomb's law for electrostatic force between two point charges and Newton's law of gravitational forces between two stationary masses both have inverse square dependence on the distance between the charges or masses. Now the question is compare the strength of these forces, okay, determining the ratio of their magnitude. So this first part is important, even the second part is there. So for two protons, okay, for two protons and estimate for two protons actually. They have asked you to find out for, okay, so yeah, so two protons and then estimate the acceleration of the electron and proton due to this electric force. Look here. What is electric force? E square by, so this is actually, suppose between a proton and an electron, what is the force? Between proton and electron, what is the force? So I'll write uh, this way. Uh, this will be obviously an attractive force, right? So Fe will be minus E square by 4 pi epsilon naught R square, right? And Fg, that means the gravitational force, right? So gravitational force, if you are not able to see my screen, you may see your book also, okay? The first example in this Coulomb's law. So what is the electric force? Electric force will be minus E square by 4 pi epsilon naught R square. So R actually they have given you, suppose 1 angstrom, okay? Suppose 1 angstrom away from each other. And masses of the proton and the electrons are given. Okay, G you can find out from your you can find out from your book what is the, it is actually having 6.6 into 10 to the power minus 11, okay, in SI unit, gravitational constant, okay, and this actually 1 by 4 pi epsilon naught, it will be having 9 into 10 to the power 9 Newton value, okay. This is 1 point, E is equal to 1.6. So if you just find out the value of these two, look here, so you will get actually Fe by Fg, the ratio of electric force to the gravitational force is found to be 2.4 into 10 to the power 39. That means your electric force is almost of the order of 10 to the power 39 greater than the gravitational force. That means when two charges will be just falling from certain height to down, okay, in an electric field, constant electric field or uniform electric field, that time the force experienced by that charge will be actually due to the electric force, not the gravitational force. Okay, the rest of the part you will just see here. I'll just tell you another example here to why I'm talking. Okay, just the next one. I think this one. Okay, so not this one. Another example is here actually. Suppose I don't know. It will be somewhere. Okay, I'll tell you later when I find out that example. Okay, so this example is important anyway. Okay, so what is the ratio between electric force and gravitational force between two charges? Okay, so these two, this example you look here, and okay, this I think you should see. I'll just tell you another fact about this force. See, now we have learned so far. We have learned electric force, the Coulomb force between two forces. I'll just go for another 5 minutes. Then I'll just stop the class. Okay, just be patient because this part I'll just discuss. Then I'll stop it. So we have learned so far electric forces for or Coulomb forces for two charges. But if suppose there are many charges, okay, many charges. Here, look here in this figure. I'll just enlarge it. See in this figure, there are how many charges? Like Q1, Q2, and Q3. There are three charges. So how do you find out the Coulomb force in that case? Because see, any force, see that there are charges Q2 and there will be force between Q2, Q3. There will be force between Q1 and Q2. There will be force between Q1 and Q3 as well. So how do you find out the force, total force or the net force? See, in this case, there is something called superposition law of superposition. What is that? The law of superposition states that when there are multiple charges, okay, when there are multiple charges, if you want to calculate the net force due to, like a net force on any particle due to all other charges, like on suppose on Q1 you want to find out the force due to other charges Q1 and Q2 and Q3. So that time what you can do, individually you can find out the force. Like see, I'll just consider Q1 and Q2 first. and that time I'll not consider the presence of Q3. When I consider the force between Q1 and Q2, I'll not see the I'll not see the Q3. That means I'll neglect the presence of Q3. And when I'll calculate the force between Q1 and Q3, that time I'll neglect the presence of Q2. That means I'll not consider the presence of Q2. So like that, if you have many charges, like see here, there are many charges. I can find out the forces. See Q1. See, they will ask you to find out the force on Q1 due to all other charges. So what you just find out the forces, individual forces, like for charge 2 what is the force on Q1, for charge 3 what is the force on Q1, for charge 4 5 and etc. And when you find out all these forces, you just take the algebraic sum, sorry, vector sum, not algebraic sum. You have to take the vector sum. See, you have to take the vector sum of all these forces. Then what you get is called the net force. So see, this is actually called superposition principle. See, it is verified that force on any charge due to a number of other charges is the vector sum of all forces on that charges due to the other charges taken one at a time. Taken one at a time. Do you understand? Taken one at a time. The individual forces are unaffected due to the presence of other charges. This is termed as principle of superposition. So there, see, they have calculated, see, the force on Q1 charge due to all other charges Q1, Q2, Q3, etc. So what they have done, they have calculated the forces, individual forces, like when they consider the charge Q2, they don't see all other charges. They just they calculate the force on Q1 due to Q2 charge alone. So F12 they have calculated. Then for the 3, okay, for like due to 3, what is the force? F13. Then similarly F4 also they have calculated, and and if you have such n number of charges like that, you can calculate the individual forces and take the vector sum, not the algebraic or scalar sum. You have to take the vector sum. Okay, not necessarily there will be always positive charges, there will be positive negative mixture also. So I'll just take you one example. See, I'll take you through one example. Suppose there is a equilateral triangle, and at the vertices there are 3 equal charges. Then you have kept another charge capital Q at the centroid of the triangle, this equilateral triangle. Then what is the force experienced by this capital Q due to all other charges in the vertices? So can you tell me what is the force experienced by this capital Q charge at the centroid? Look how you have to do. I'll just take this figure here. I'll just copy this figure. Go to the slide show. Are you people able to see my screen?
Yes, sir.
Yes, sir.
Okay, just 2-3 minutes, then I'll stop the class. Okay, I'll just explain this, and it is from your book only, so you can read by yourself. I'll just explain it and then I'll stop. Okay, look, so the question is, this is an equilateral triangle. See the length of the sides AB and then BC equal to AC. These are all having L, okay, sides. And there are, see, 3 charges on the vertices Q1, Q2 and Q3. These are all having actually same magnitude Q. Okay, Q1, Q2 and Q3, they are having same magnitude Q Coulomb, suppose. And another charge capital Q has been kept at this centroid. So what is the force experienced by, net force experienced by this capital Q charge, which is kept at the centroid of this triangle due to these charges on the centroid? So in this case, it is very easy to solve. Okay, very easy to solve. First of all, you have to take, see, see, you have to consider the principle of superposition. Principle of superposition. Okay, principle of superposition. So what was that? What was that? That was actually you have to consider any two charges, and at that time other two charges you can neglect. Suppose I'm just taking I'm just considering the charge like force on capital Q due to Q1. That means I have capital Q over here and Q1 is here. So and see I know the distance because okay, let me see what is the so which direction the force will be? It will be repulsive force, right? So the force will be which direction? This direction. It will be pushing. So this is F1, right? Right or not? So the direction will be this way, right? That time I'm not considering. See, if I want to know the magnitude also, I can know Q1 and capital Q by 4 pi epsilon naught, whatever distance it is. Okay, that distance square house. It will just like that. Okay, but I don't need to require also actually here. The Q1 I got Q1. Sorry, F1 force on Q due to C. This is shown over here. This is F1 due to Q1. It is repulsive force, that's why it is downward. Okay. Now the force on Q due to my Q2 charge. See, in this way it is. This is capital Q. This is Q2. So this force is this way. Okay. So this is here. Now my Q3 is here. So my Q3 is here. So this is Q, capital Q, and Q3 is here. So the force will be in this way. Look here. This is a Q3, this is Q2, and this is Q1. Now what I'll do, this actually see, this also Q, and this is capital Q. This also Q, and this is capital Q. So magnitude of the force, all F1, F2, and F3, their magnitude will be same. Do you agree or not? Because the charges are same. And distance also will be the same actually from B to C. See, this is the centroid. From any vertices to centroid, the distance will be the same. See, like AO, if it is O, then AO will be equal to BO equal to CO. So the distance, this is O, this point is O, this is AO, and this is BO and CO. So the distance from the vertices to the centroid, from each vertices to the centroid will be the same. Okay, that means the magnitude of this all forces will be the same. Okay, magnitude of the forces will be the same. Now I have to take vector sum. That means F1 vector plus F2 vector plus F3 vector. I have to take vector sum. I am applying superposition law. I have calculated the forces, individual forces. Then I am taking the summation of that. That means I am just taking sum. Okay, this is about all about superposition principle. Now I have to see how I can add here. See, I have three forces. I'll just see, write this as, look, this is actually F2. See here. Okay. And look this way, it is F1. And look this way, it is F3. And in fact, all these forces are equal in magnitude that I have shown you. Now, if I want to take component, okay, along this vertical direction, suppose Y, and this direction X. So I want to take the component of all these three vectors, okay, along these two directions. So if I take component of F2, one component will be this way. F2, I'll take a right parallel component and perpendicular component along this way. F2 component perpendicular, right? Now look, this this F3. So if I take component of this, one component along will be along this way, F3 perpendicular, and another component will be this way, F3 parallel. Okay. Look, these two forces are equal in magnitude. That means these two components. If I say this is 10 Newton, this also will be 10 Newton, and they are actually cancelling each other. Understand? They are cancelling each other. Now look, if I say 3 is actually, see, this F2 has component along this way. So F2 perpendicular component plus F3 perpendicular component will be such that their sum will be equal to the force of F1. Okay, so which is downward direction. So you will see finally this F1 will be cancelling, like F1 will be cancelled by this net force between this F2. This is F net. This F net will be cancelling whom? F1. Okay, F net will cancel. F net will cancel F1. Okay, because these are two in opposite direction. They will cancel each other. So what will be the net force acting on capital Q then? It will be 0. So it will not experience any force at the centroid. Understand? So F on Q, force on Q will be 0. Force on Q will be 0 due to all the charges. So I think I'll stop it here. You can just read your book, textbook, whatever I have taught you, everything from the textbook itself. And these examples you see in your book, like how it is solved. And if you don't understand, there are many examples as well in between whatever I have taught. To see all the examples, because all of them are helping you to understand the concept very well. Okay, please read the text as well as the examples also. Next day I can ask you. Okay, I'll see how you are understanding. So now I'll just stop this class today. I will meet again on Sunday. Okay, so in between you people have to read whatever I have taught so far. Okay, okay then. So this is all for today. Bye bye.